Hi, and welcome to linearization. So what we're going to be doing in this lesson is we're going to be taking curvy lines and we're going to be making them straight lines. Doesn't that sound cool, Mel? She likes that idea. That's because we're finding the derivative at a specific point. So if we're finding the slope at that point, can we use that to make a line? The answer is absolutely. We're also going to be starting with the differential, which is going to lead into this thing called related rates that we're going to be doing for the next couple days after that. So check it out. This is what it means to create the linearization. So it's finding the tangent line at a particular point. You might recognize this as, what's that thing? Point slope form. So here is like a y value, that f of a. It's been brought over to the other side, that L of x, that is a y value. And then the derivative, that is the slope of the tangent line. So that is our m. And then you've got your x2 minus x1, or x minus x1, excuse me. So this is finding the approximation of a straight line at that point. It's not going to be perfect, Mel, but it'll at least be kind of close to what's going on. And here's kind of what I mean. Here's our first example. I have this equation, f of x equals x cubed, blah, blah, blah. And I want to figure out, okay, this is a curvy line, but if I look at just at 2, what's going on? Am I able to turn that into a straight line? So I actually made a graph of this thing. So here's my graph. And here is 2. And I want to look at the graph right at 2. So that's right at this line. Well, as we zoom out, it's kind of a curve. Like it's more curvy over here, but it's still pretty curvy over there. But as we zoom in on this point, see how it sort of starts to form, it looks like a straight line now if I'm looking at just that spot. And that's what we're doing with this linearization thing, looking at a really tiny part of the whole curve in order to turn it into a straight line. Sorry if you need to rewind this because my cat is too distracting. So we're going to try this out. We just need to plug stuff into this formula that we were given. So L of x, because they're asking us to figure out what L of x is. And then we're going to do this when x equals a, and in this case, our a is going to be 2. So we need to figure out what f of 2 is. So here, I'm just going to write this all out first. Mel, you've got to go now. I'm sorry, but you've got to go, okay? I know, she's so upset. So we want to do f of 2 plus we need to do f prime of 2 because we need to do f prime of a, and in this case our a value is 2. This is going to be multiplied by x. That's always just going to be an x, and then our a value one more time, which in this case is 2. So we just evaluate all of these things. So it's just a matter of plugging and chugging. So if we do f of x, so that is something cubed minus 2 times something plus 3, or something in this case is 2. Plus we need to do f prime of something. So I'm going to write that out. So that is 2, oh, not x, 2 times something, because I'm going to put another 2 in there in a sec. 2 times something squared minus 2 times something, and then that 3 goes away. And then we still have our x minus 2. But we want to make sure that this whole number gets multiplied by that parentheses. So I'm going to wrap that derivative up in parentheses, or you could put a bracket too, that works. So this thing is 8 minus 4, that's 4 plus 3, so then that's 7. Oop, I forgot to put in these 2's. And then that is 8 minus 4, so that's going to be 4. Wait. There should be a 3. Good thing I have my key. So that is 4 times 3, which is 12. Minus 2? Oh, yeah, there shouldn't be that there. Oh, kind of making a mess of this. We get 10. X minus 2. All So L of x equals, and I'm just going to distribute and simplify this thing out a little bit. We get 10x, and then we get negative 20 plus 7, so that is negative 13. Cool. So this is what they're looking for in part A. Part A done. We found the linearization at that particular point. We want to figure out how accurate is the approximation L of A plus 0.1 to F of A plus 0.1. So as we move away from that point, how accurate are we staying? So our A value is still 2. So we need to figure out how L of 2 plus 0.1, see how closely that is related to F of 2 plus 0.1. So L of 2.1, if you just plug that all into your calculator, and I'm just going to kind of skip that part for time, you get 8. And I'm just plugging 2.1 in for right there. And then for F of 2.1, I am just going to plug 2.1 into all of these spots and see what that works out to be. Plugging it all to my calculator, I get 8.061. Now it's asking how accurate you want to find it. In order to figure out how accurate you are, you need to find the difference between the two values and their absolute value, the absolute value of the difference in the values. So the absolute value of 8 minus 8.061 equals 0.061. Then we count how many decimal places stay 0. So this first one stayed 0, but then after we got to the next one, now we're off. So since we had one thing that we're off by a 10th. And to say the 10th, we're actually going to write it as an exponent, because 10 to the negative 1, that's a 10th. If you kind of like do your exponent rules. If we had gotten 2 decimal places to be 0, then we would have done 10 to the negative 2. But since we only had 1, we do 10 to the negative 1. Because, yeah, that's 10 to the negative 2 is when we started getting a different value. Let's try another one of these. So once again, we want to find the linearization at a particular point. I'll make sure I've got my key handy. So it's just another matter of plugging and chugging. So we're doing L of x equals the f of a. So in this case, we're doing f of 0 plus, we need to do f prime of a, which is, again, 0. And then we need to do x minus our a value, which is 0. So this is just going to end up being an x when we're all said and done. So L of x, we need to do f of 0. So then this is going to be the ln of 1, because we do 0 plus 1. That's 1. Then we need to do the derivative of f of x, and we need to plug in 0. So that is going to be, let's see, the derivative of natural log. So that is going to be 1 over the inside multiplied by the derivative of our inside. But the derivative of x plus 1 is still x plus 1. So it's just going to stay 1 in the numerator. And I did want to plug in 0, so I'm just going to kind of scribble over that x and make it a 0. And I didn't need this x all the way over here, so just come on over here, x. Cool. Now let's figure out what some of this stuff is approximating to. So the natural log of 1, if you put 1 into a logarithm, you get 0. So the ln of 1 is 0. Plus, we have 1 over 0 plus 1. Well, that's just a 1. So it's just x. Well, 1x. So the ln of x equals just x. Neat. So at that point, we're basically turning into a straight line. Mel is actually still in here with me. She's on the floor right down there, and she's just like glaring at me. No, you can't see. You can't see. You can almost see, but she's just glaring at me and she's like, "You play with me." No, we're recording videos. Now that we found the linearization, we need to figure out what the how accurate it is as we go 0.1 away from that point. So let's find out. So we need to do L of 0 plus 0.1, and we need to do F of 0 plus 0.1. So L of 0 plus 0.1, that's pretty easy. That is going to equal just 0.1. F of 0 plus 0.1, that is going to be the ln of 0.1. Yeah, ln, oh wait, sorry. It is x plus 0.1, so that is 1.1. Sorry, my brain fell apart for there for a second. I was like, no, my key's got 1.1. Why am I not getting that? I forgot. The original equation had ln of x plus 0.1. Okay, so the ln of 1.1, we can type that into our calculator and we get 0.095. Okay, so let's find the absolute value of their differences. So 0.1 minus 0.095 equals, I actually don't have that handy, so I'm going to do that real quick. 0.1 minus 0.095. So 0.005. Okay, now there are 2 decimal places that turned out to be 0, so our approximation differs by less than two, less than a 100th. So approximation differs by less than 10 to the negative 2, 100th.